All right. Welcome to lecture 11, I think it is. Sorry I didn't finish grading the quiz. I'll give it to you tomorrow, definitely. Okay, so yesterday we we did a bit of derivation to compute the quantity, the propagator, whose definition is that is the amplitude for a particle to propagate, particle with Hamiltonian age, to propagate from a point x0 at time t equals 0 to a point xn at time capital T. And it's well defined, and today we will be calculating it in some simple cases. But we found that this is equal to a strange thing. So we'll put a little question mark and a little exclamation mark here. It's equal to the integral, multiple integral, over the following measure. Yesterday I think I wrote product over x. Of course it's not a product over x. What you probably remember in this derivation is that there's a dx integral at each time step. So the product is really over t, all t between 0 and capital T. So there's an independent measure at every t. Of course if epsilon is finite, then it's only this product runs over t1, t2, t3, all the different time steps. But in the limit it becomes a continuous product, which we don't really know what it means. Okay, this. But then the thing that we are supposed to integrate is e to the I times the action divided by h bar. And that we certainly know what it is. Okay, is the action evaluated along that, along each trajectory. So for every, so this is one way to write it. This is the way we reached, and it has two problems, two obvious problems or visible problems. One is the presence of epsilon here, since we are supposedly taking it to 0 and putting epsilon squared to 0 on the way, it shouldn't be hanging around. And there's also an epsilon dependence in this product because the time runs in epsilon steps, okay, t by capital N, and so there's a dependence on epsilon there, and somehow we want all this to go away, but it's not gone away.
Sir?
Okay, yes.
Sir, in the exponent we got the action times dt.
Yeah,
so like,
not action times dt.
Lagrangian times dt.
You got Lagrangian times
And
dt.
so the action only comes when that product goes inside, right?
No. But what we did was, because this is in the exponent, a product can be replaced by exponent of the sum.
So, but like the product and action both are written. We should write only one, right?
So this is inside here, and the action is just once outside. Huh? Yeah, that's not inside the product. Correct. Okay. Now, as I emphasized before, and I'll keep emphasizing, when we reach a stage like this, at least people who are really creative scientists don't give up. They first look for the good aspects, and obviously you're not going to find those good aspects in this measure, which is a mess. The good aspects, if there are any, should be here. Well, one of the interesting good aspects, which you can read right away, is that it depends on L rather than H, Lagrangian rather than Hamiltonian. So in a way we might say that, well, all our quantum mechanics, we know that in classical mechanics, Lagrangian and Hamiltonian are just equivalent ways of formulating a problem. We have Lagrange equations, we have Hamilton equations. Which one we prefer depends whether we are French, then we like Lagrange. If we are Irish, then we like Hamilton. If we are neither, then we can pick either one. But the fact is that both of them work. Now in canonical quantization, we really stick with the Hamiltonian. It's very central to canonical quantization. We pick some time direction and we evolve, and then evolution is by the Hamiltonian, and that's why it's sitting here. It becomes an operator, and it is the centerpiece of canonical quantization. So now instead of favoring this so much, we are now favoring this, so it seems to restore some balance. Maybe in life, we should have, for every Hamiltonian thing, there should be a Lagrangian thing, maybe. It's not that simple, but it's a nice thing. There's a much deeper reason. What I said was a little superficial. There's a much deeper reason why Lagrangian is better than Hamiltonian, which you already know, that in field theory, the Lagrangian is Lorentz invariant, but the Hamiltonian is not. The Hamiltonian is only defined when I pick a direction of time. Under Lorentz transformations, the direction of time will change because time mixes with space. So I'll get a different Hamiltonian for every different Lorentz frame of reference. The Hamiltonian for me sitting on platform of a station is different from the Hamiltonian for the person in the train, because their definition of because their frames are boosted. Okay, once you boost a frame, then the definition of time changes.
So,
but yes.
So in there we want some manifest Lorentz invariance, like covariance, right?
Yeah.
But here, like in non-relativistic.
No, this is non-relativistic. I'm anticipating something that we'll be doing. If we did field theory, yeah. Here we don't. Of course, we don't see that
Because
here there was never any relativity to start with. But in field theory, and so this is a kind of little bit motivation leaping into the future by 2-3 lectures. We know that L is Lorentz invariant and H is not. And the fact that this depends on S, which is integral L dt, it will, in field theory, it's not a surprise, this will be integral of L d for x. And d for x is also Lorentz invariant and L is also Lorentz invariant, so S is Lorentz invariant. And it's a good thing because in field theory, Lorentz invariance is very fundamental and we don't like to give it up unless we have to. So maybe the path integral will be a better way to quantize field theory because it will preserve Lorentz invariant. That's a guess we could make, and that guess turns out to be true. It's a very important reason. Okay, so this is one of the good things. One of maybe the short list of good things about this. Okay, but there's a second good thing, which is the limit h bar goes to 0. It's well known that when h bar goes to 0 relative to other quantities in the problem, you are in the classical regime. Okay, it's the regime also called large quantum numbers. You are not in the near the ground state of the system. You are in some excited state, or you have large number of objects, and the quantum discreteness sort of washes out or averages out. Okay, now in that limit, we certainly think that the classical theory should be true. So this is called the correspondence principle or something. So can we see in this that it will be true? And we see that because this is an integral, whatever this measure might be, it's an integral over an oscillatory function. Right, this will oscillate as the value of S changes. Because of this I here, this is going to oscillate. It's a phase. Okay, and in the limit h bar goes to 0, the phase diverges. This is the phase and it diverges. But we know from experience with ordinary integrals that when that happens, the dominant contribution to the integral comes from the stationary point of this thing on top. This is called the stationary phase approximation. We'll be actually discussing it. And in this case, it tells me that the variation of this action functional with respect to x should be 0. Only when that is satisfied, then this will contribute to the integral. All the other values of s which are not stationary will cancel each other's contribution out. This is something you might have encountered, but if not, we'll be doing it. You can also see it another way. You can imagine that this I is not I but minus sign. Okay, that happens if we are going to soon do something called Euclidean continuation. Briefly, we discussed it once. When we send time to imaginary time, this I will turn into a minus sign. You can see it sort of because this is integral L dt. If t becomes I tau, then this is minus. Okay, now you can see that if h is going to 0, the only s which will contribute is the minimum one. Okay, all the others will be exponentially suppressed. So again, s has to be stationary. Okay, but what is this equation? Is exactly the Lagrange equation of motion. Okay, and this tells me that we recover classical physics. So this is the second reason to be happy, which is that anything which is an integral over an exponential of I times the action divided by h bar comes built in with the feature that when h bar is small relative to the action, only stationary action contributes, and we are back to classical, and therefore the equations of motion are satisfied. Note that otherwise, if h bar is not small, we have never said that equations of motion should be satisfied in this. So when we integrate over these x's, we are not saying anything about the path x satisfying equations of motion. So in that sense, this h bar goes to 0 limit is nicely built into the formalism. But still, this is problematic, and now we'll learn how to deal with it. Yes?
So in the second case, there is an h bar in the measure in the denominator also.
Yeah, you know, the point is that this denominator is something that we are going to, you mean this, right? Yeah, but you know, that doesn't change anything. That can come outside the integral, right? We're trying to perform an integral.
Yeah.
So h bar outside is not going to change anything. We're trying to ask that given an integral, approximately which regions of the integrand contribute. So basically, you can just model it by imagine some kind of function. Let's say we are trying to find the area under a function, and probably I'll do a very bad job of drawing this, but if I have some oscillating function like this, maybe this is not a good example. I don't know what's a good example. Let's postpone stationary phase till we get there. But it's a valid question for any integral that if I don't know how to evaluate it exactly, can I ask which possible values of the integrand give me the most contribution? And it turns out that when because this is an oscillating exponential, there is this theorem. It's just a theorem in wave theory, it's not, or in function theory, it's not anything to do with quantum physics specifically, which says that when h bar is small, this whole thing becomes large. That makes the exponential oscillate violently. And the result of that, you know that a phase which is oscillating, sometimes it's positive, sometimes it's negative. So on average, they can cancel out. And the only place where the contributions don't cancel is when the first derivative of the function on top is 0. This is again, it's a theorem on ordinary functions. Here we are going to try transport it to functionals, which in itself is little problematic, but it will be possible. Anyway, again, these are sort of qualitative comments, and now we'll get down to actual calculations. It's just a comment about what are the good things, good features of this, both of which come from this exponential of the action. And the bad features I don't have to tell you, they are very visible. We don't really know how to define this better. Okay. So we have to take some point of view, and the point of view is very simple, at least conceptually. We simply change our rules to say that this quantity u is equal to something with a box dx e to the I s of x by h bar. And we use this as a starting point where we try to understand this measure a priori instead of taking it as that epsilon dependent thing. Okay, and we'll also, if we want, we can put some normalization factor in front. As it turns out, it won't be needed because we are going to consider quantities which are normalized. I'll explain that in a moment when we start to calculate. So we just say this is a abstract measure on the space of parts. What does that mean? Supposing there's a particular path. Supposing I fix 2 points, xi and xf, and well, we did this diagram yesterday. So this is xf at time t and this is xi at time 0. Here's one path, here's another path, here's a different path, here's another path. These are all smooth paths. Now, I didn't really find a justification why I should be talking about smooth paths, but let's assume that we can. Then, a measure means that when I have, let's say, this path, one of them, let's label them C1, C2, C3, C4. Of course, you know there's an infinity of paths, but I'm just picking some of them. For each of them, this thing is well defined, it's just a calculation. What do? I take the path itself. I know x of t as x as a function of t, which has the property that at 0 it is xi, at t it is xf. I plug that into the Lagrangian. I find the value of the Lagrangian on that path and I integrate over time and I get the value of s. So that's easy. For every path I can find the value of s. Now a measure tells me how much importance to give to each contribution. That's what a measure always is in an integral. Okay, you know sometimes you have done 3D integrals or 2D integrals on surface of a sphere or something, and you know these factors or in spherical coordinates rather, where you get this r squared sine theta d theta d phi. So when r is small or when sine theta is going to 0 or something, your measure becomes very small, and you understand that it has something to do with the nature of the space you are integrating, that in that region the area element is scaled in a certain way. So it's like that. That's what the measure is doing. So we have to find a way to assign some value to the measure for every path. That's the open problem. It should have been assigned to us because we supposedly came to this by doing some manipulations, but whatever that was, in the end it seemed to work for us, didn't give us a epsilon independent thing. But this thing that we are going to hope for should be epsilon independent. Now we don't have any epsilon, we have just banished epsilon from the game. There are no time steps, there's no derivation, this is just a proposal. And the inspiration for the proposal was the previous calculation. Yes?
So the continuity of the paths could it be related to x dot square being integrable in this?
Yeah,
because we
so
have to find out the action. So
yeah, of course. So it should be, but even if they are continuous, they need not be smooth. They could be jagged paths. And so here's a very worrying class of, you could just make a path which is really horrible, like it starts here, it ends here, and it just goes like that. What are you going to say about that? X dot would be badly defined for such a path. X is well defined, but x dot is badly defined. At each of these, it suddenly loops back. Okay, but you can't really rule it out because at each time step originally, we were integrating over this direction freely with respect to the next one. So we have no reason to think that the path went smoothly through it. So these are, every time you look at it with a physical intuition, you find some pitfall or the other. I think mathematicians have done better, and I think even in recent years there is some progress in this. but it's not something that seems to be amenable to any techniques that we physicists understand readily. So instead of that, we are going to assume that there is some abstract measure, and we'll try to see how far can we go without knowing the measure, and how much can we determine the measure by self-consistency. That would be really helpful, because we have some laws that this thing should satisfy. Just to give you one example, if I pick a measure badly, then this cannot be u, because u satisfies a composition law. U times u integrated over the intermediate x is again u. So I can't pick this very badly, and we'll see an example of that very soon. Good. So we'll start with baby steps. The simplest Hamiltonian we know is the free particle in one dimension, no potential, just p squared by 2. Now for this, we can certainly calculate u using known methods of quantum mechanics, and let's start by doing that. So I'm going to call this UFP. FP is for free particle. Okay, so for this Hamiltonian, and I'm going to write it like this. We'll have, at this end we have xi and 0. Now we have to insert a complete set of energy eigenstates, and for a free particle, energy eigenstate is the same as momentum eigenstate. So I just use k, where p is h bar k, or you can call it, you can have p if you take it. Yeah, 1 second, let me finish writing this. Yes.
So if we choose a free particle,
Yes.
the phase space available to the particle is like the entirety of x and p.
Yes.
But if we started with a potential where the bounded solution is allowed,
Yes.
then that reduces the phase space. So will the outcome of the calculation somehow affect?
Slow down, slow down. We are doing free particle, then we'll do harmonic oscillator, then we'll do something else. We'll learn every case. We're just starting with one case. So we can't conclude anything from one case. We'll find some nice features when we do just two cases, this and harmonic oscillator. But if you want to do particle in a box, you can also do that. You will get some answer, and it might be illuminating. This is why all these are like the toy quantum mechanics problems that we learn quantum mechanics from. I agree that in a way this is one of the less typical ones. Maybe the one with the potential is more typical. But anyway, we do encounter this, so we should just do all. Okay, so in this case, now what do I do? Well, this, and I have to integrate over k and k prime. So I've just defined k such that p is h bar k. That saves me writing a lot of h bar factors. Okay, so now this, so let's go step by step. This thing here is 1 by root 2 pi e to the I kx f. It's the overlap between the momentum space wave function and the position space wave function. So that's nothing but the momentum space wave function in the position basis, which is, as you know, for a free particle is that. Okay. Likewise, this last factor will give me minus xi. Same thing with minus x. Sorry. Not yet. Yeah, not yet. Yeah.
K prime.
Yeah. So e to the minus I k prime xi. We'll get a delta soon enough. Okay. Now for this thing, the h will evaluate to this. So p will evaluate to k prime or k, and then there will be a delta k prime. So I'll get delta k prime and e to the minus I h bar k squared upon 2.
Sir?
1 second. T.
Sir?
Yes.
That's the delta function, not
Okay.
because that integral.
You're quite right. Eventually in physics we become so sloppy that we don't distinguish this delta from that delta, but we should. Definitely there's an integral, yes.
Another factor of 1 is 2.
Yes. Perfect. Good. So we agree on everything now, and when we collect everything together and we perform the integral. So first one, k prime integral will get rid of the delta function, and then k integral will be a Gaussian integral on this plus a linear term. So we'll get something, and what we get, I'll have some comments about the K integral later, but first let me write the answer. So I emphasize no path integrals have been used here. This is a simple quantum mechanics calculation for a free particle. It's just that this question, what is the propagator, is not normally studied that extensively in quantum mechanics courses, though it should. But if you did study it, you would get this thing. Okay. Now there's one subtlety which is actually reminiscent of something we already saw, which is that when we integrate over k, there's an I over here. So it's not strictly the normal Gaussian that we are used to, which should be integral dk e to the minus k squared, because there's an I. And that little bit spoils it, but it's a standard thing that we can just imagine shifting k slightly into the complex plane so that this becomes damped. Another way, practical way, is to just package I h bar over 2m times t, just call it a, and pretend some number a and pretend that it's real. Then you have e to the minus ak squared. Then you can do it, and then finally you put that a to be this imaginary number. That's why you get the I here. Okay. So this is an answer. Now the challenge is how to get this from path integrals. Good. So before we address the challenge how to get it from a path integral, let's just save this answer at the top and start again with a different problem, and then we'll see what's going on. So u free particle, I won't write the arguments anymore, is square root of m upon 2 pi I h bar t e to the I m over 2 h bar t xf minus xi squared. By the way, notice that since there was no potential, the particle is free to go everywhere, as Sayan already pointed out, and therefore the only thing it can depend on is xf minus xi, the difference, because we could shift both the starting and end points without really changing anything. So it's natural. And now we'll simply do the same thing for a harmonic oscillator. So now we are going to write U harmonic oscillator HO, and for that we are taking the Hamiltonian to be p squared over 2m plus half m omega squared x squared. Now I shouldn't have to write out the calculation because it's essentially the same. There's at the beginning there's this xf with some psi. But now the psi is a stationary state of the harmonic oscillator, so it is labeled by the integer n, which tells me the harmonic oscillator state. Then psi n e to the I h t over h bar psi n prime, and then psi n prime xi. And now actually, because these are discrete, I have to sum over n and n prime. Good. So what are these? These are the position space wave functions of the harmonic oscillator. This one is psi, this one is psi star. And here I'll get delta n n prime, actually Kronecker delta, and then here I e n, which actually I know, n plus half omega t, and the h bar is gone. H bar omega, so h bar cancels it, and then I put
There's a negative sign.
negative sign where?
E minus.
Here. Then there's also here. Okay. Good. So this. Now what would be the next step after this? So one n summation is done. This goes back to n. So this is psi n squared. This is gone. And this is the weight, and I have to perform the sum over n from 0 to infinity. See why 1D harmonic oscillator is so nice. It doesn't have any degeneracies or anything to worry about. There's one state for every n, and this is the answer. Now to proceed, what should I do? I need to know psi n of x, and you know what they are. They are the Hermite polynomials. So we put those polynomials in and we calculate and we get an answer. Now, since all of you are nodding nicely, I will invite you as an exercise to do the calculation. I'll only write the answer. It's really as straightforward as it can be. I am suppressing the argument of this, but you know the argument, it is xf and t and then xi and 0 always. So, when we do this, it's not very hard. We get this answer. Something pretty big here. M omega E is really such a pretty answer that you really should have done this in an earlier quantum mechanics course. There. That's the answer for the harmonic oscillator. Now, what can we notice about the answer? First of all, doesn't depend on xf minus xi, but separately on xf and xi. Why is that? Harmonic oscillator has a center about which it's oscillating, so it does matter where you start and end. Okay, so that. Then it depends obviously on the frequency of the oscillator omega, but it has a very cute feature which should be true, but we couldn't have been sure perhaps till we saw it happen. What happens in the limit omega goes to 0? Just by visual inspection, you'll see that this goes to that. Here sine omega t becomes approximated by omega t, the omegas cancel, and you get that. Here cos omega t is 1, and once you put 1 here, then this whole thing just turns into xf minus xi squared. So this is a nice check that this is a correct calculation because its omega goes to 0, which is good. Okay. Okay, so these are, yeah.
4xi xf.
Yeah.
Sorry. That's a good point. Sorry, no, I wrote something wrong. Okay, this is what my notes say. Okay, good. Now our challenge is to reproduce this by doing a path integral. So we have, instead of one problem, we are trying to reproduce two problems. Both of these answers are absolutely correct because we have derived them by very well-known principles of quantum mechanics. And now we'll try to find out u fp as the integral over some measure e to the I s of the free particle, where s of the free particle is integral dt from 0 to capital T of half m x dot squared. And the same thing we'll be trying to do for the harmonic oscillator, and only thing we'll change this to this term minus m omega, half m omega squared x squared. Okay. Now, as I said, we don't know this measure very well, but this is now Gaussian in the variable x, in the function x actually. Okay, and we are going to use that inspiration and some knowledge of Gaussian integrals to make a guess how this is done. Before we do that, so I'll just make a comment here that this some Gaussian type of functional integral. Both of them are, because in both cases one depends only on square of x dot, the other case harmonic oscillator has x dot squared and x squared, but it's only squared, there's no x cubed or fourth power or something else, so we can be a little bit hopeful. So now let's recall a result with multivariable Gaussian integrals, and the result is, supposing I have, this is just result in ordinary integration. Supposing I have p independent variables x1 up to xp, and I give you the following quadratic form to integrate: minus half xm omn xn. This kind of integral is familiar. I'm not going to write the summations, so m and n are summed over, each of them from 1 to p. Do you know this integral? It's an n variable generalization of Gaussian. It's a very standard integral. How would I try to evaluate this?
Diagonalize over.
Very good, thank you. So I just use a similarity transformation to go to some y's, and here I would get lambda n yn squared, where lambda are the eigenvalues of O.
Some
Yes.
Because we are doing a change of variables.
Yeah, but we are doing just, we can just do it by orthogonal transformation. I see this is a real symmetric matrix. So we can diagonalize it by, it's real symmetric Y. I'm choosing it to be real. And as far as symmetric, because it multiplies xm and xn, so the sum effectively symmetrizes it. Okay, so it can be diagonalized by an orthogonal transformation which has determinant 1, therefore there is no Jacobian. So far so good. Thank you. Very good. Okay, and now the answer of this is product over all the number of variables, lambda n upon 2 pi to the minus half. So it's root 2 pi upon lambda n, but I'll just write it like this, because if this was just a single variable and this number was a, the answer would be root 2 pi upon a. So this integral is from minus to plus infinity. And same here. Okay, so this is the answer for a multivariable Gaussian. But now we notice that actually diagonalizing helped us to do the integral, but we can rewrite the answer again in terms of O, because this contains the product of all lambda n's. So what is the product of eigenvalues of a matrix? Determinant. Superb. So this is also equal to det to the minus half of O upon 2 pi. Good. Okay. Now we want to transport this result to the path integral case. So we need to find the analog of O. And then if we want to evaluate the answer, first let's find the analog of O and get the answer into this formal form, and then we'll think about what are the eigenvalues of that O and get it into this form, and then we'll try to evaluate it. Okay. So the first step here is to try and get the path integral to look as much as possible like this sort of integral. So now I can rub this out. I think these steps were crystal clear to everybody. So I'm going to rub this out. It's all in the notes. So I'm going to keep writing dx here without knowing exactly what it is. And here I'm going to write e to the I by h bar. And now I have 0 and t dt m x dot squared. So 2 here. I would like to do one integration by parts and bring this to the form minus m x of t del t squared of x of t. Would you agree with this manipulation? Just take one of the dots from one of the x's and put it on the other one. There's a small problem. Boundary term. So the problem is that x is not vanishing at 0 and t, it's actually giving me xi and xf. So before I do, so I want to do this, but before I do this, I'll do something else to get rid of boundary conditions. And though it looks just like a simple trick to get rid of the boundary terms, it's actually quite deep. So I'm going to say that let an arbitrary configuration x of t be written x of t equals x classical of t plus eta of t, where this one is a solution of the classical equations. So what am I doing? I'm taking the set of all possible functions x of t which start at xi and end at xf and decomposing it as a particular classical solution that starts at xi and ends at xf, and then a fluctuation which starts at 0 and ends at 0, because when I add these two, the whole thing should again start at xi and end at xf. So the fluctuation, this one, we'll call it a fluctuation, though that's not a good term yet, but it will become, is going to satisfy eta at 0 equals eta at t equals 0, while this one is going to be a solution of the classical equations with the given boundary condition. X classical is equal to xi, or x, I don't remember, I'm calling it I now, and x classical at t is xf. Okay, this is nothing more than a change of variables in this integral. Its integral is over all x's. If I pick one classical solution and shift x by that, the integral becomes over all etas. Because this is like a fixed thing. We are not integrating over it. We are picking one classical solution. Now you may say that's not enough. Maybe I should pick many classical solutions. But in the problem at hand with these boundary conditions, there will be one simple classical solution and this will be enough. So we'll worry about more classical solutions when we come to it. Okay? So the idea is clear. So if I do that, the following, and I haven't explained why I require this to be a classical solution. It could have been anything which has these boundary conditions, but with a classical solution, I'll get a very nice benefit. What's the benefit? When I expand S of x, so S of x becomes S of x classical plus eta. That is S of x classical plus a term delta S by delta x at x classical times eta integrated over the common argument plus delta 2s by delta x. So this is at some t, this is at some t, and there's a dt. And then I'll have delta x by delta s by delta x t prime, eta of t prime. There should be a half, and it should be integrated over dt prime. And for an arbitrary action, this will go on forever. For the action of interest to us right now, it's Gaussian, so this is the end of it. There won't be anything higher than eta squared. Okay? But the nice thing now, you can see immediately what my x classical has given me. Can you see? 0. This is just 0 because I chose classical. So my action, which is the central object, the object that sits here in the path integral, has split into one factor which comes out of the integral and one factor which depends only on the fluctuation, not depends only, sorry, that I shouldn't have said. Through this it will depend on the classical solution, but whose variable is the fluctuation eta, and that's what I'll be integrating over, and then I'll do Gaussian integration. So let's do that. So after this, we can simply write that this is e to the I s classical upon h bar integral d eta and e to the I, and now I have to write down what is the last term, this one. Okay, so let's look at s. If I differentiate it with respect to x, I get a derivative d by dt of x dot. And when I differentiate it with respect to x again, I just get derivative of delta function. So maybe it's easier if I write it for you. So let me write it out explicitly and then we'll see if you're convinced. So I'm going to write it as e to the I I'm going to write it as e to the minus half integral dt prime both from 0 to t O of t prime eta of t prime. Let me rub out some of this. Where O, apart from some factors of I and H bar, which I have absorbed inside O, it's basically the second derivative of S with respect to x and x at t and x prime at t, x at t prime, sorry. And I claim that in this problem, the free particle problem, we have to take del by del x of t, del by del x of t prime of integral. Now we have to be a little careful because the integral should be over dt, but we already used t and t prime, so we'll call it some new name u, and then half m dx by du squared. And now it's a functional differentiation. It's very much like the differentiation we do in field theory, but a simpler version. So I have to vary this function x of u by x of t, and I'll get delta of u minus t, the rules of functional differentiation. Okay, and I have to do that once for each of these two factors, and this answer will come out to be I m by putting all the factors together, del by del t squared of delta of t minus t prime. So once you understand this, everything else will fall into place. This is a step which I think it's best if you do yourself. If you look at that appendix, I've given you one appendix A which describes functional differentiation of fields. You just have to specialize to the case where the field is replaced by x and the coordinates are replaced by t or u. Okay, and then just do it. But can you see roughly what is happening here? I think the easiest way would be to see what's happening here by taking this operator, which I claim to be O, and putting it back here and seeing if I get the right term in eta squared. Okay, what will happen? First of all, you'll have I m over h bar, all will sit nicely outside. Okay, then here you will have this second derivative in t acting on delta of t minus t prime, and then eta at t prime, and integral in dt and dt prime. Okay. Now we want to perform the integral in t prime and then in t. If I perform the integral in t prime, then a delta would have set the argument of this to be t. But it's not a delta, it's a second derivative of delta. So what it does is it sets the argument of this to be t, but it also differentiates it twice in del by del t. So I get eta double dot. And then with one integration by parts, I get eta dot squared, and times the factors outside. That's what I had. That's what I wanted. I hope you can see that. You have plenty of time to work it out. It's in the notes also. Okay. And so my main conclusion from this is that O for the free particle is this. So how does it differ from a matrix for which we learned how to do Gaussian integration? The difference is that instead of a matrix with indices mn, this is a differential, this is a kind of continuous form of a matrix with indices t and t prime. That's really all it is. And since it has two indices, you can sandwich it between two functions, and then sum means integral in this case over the index t and the index t prime, and you are allowed to do integration by parts freely because we chose these etas to have a boundary condition vanishing at the start and end point. So that isn't a problem. Okay. So once we accept this, then we can forget about how we got there and write this as an integral. So I'm just going to do that. Any questions?
Sir, I missed the part of what exactly is U?
U is just a variable. It's a variable being integrated from 0 to t. It's just another time. See, in the action I had integral dt of mx dot squared, right? So if I rename t as u, you can't object. It's the same integral and it's the same.
If it was some other.
It's some other because I already have t and t prime. It's like if I have some discrete indices I and j, then the next one has to be k. If I call it j or I, I'll just get confused. I just renamed it for that reason. You could call it t double prime. Maybe that's more standard. Just a rename. Because we want to call these as t and t prime. We could also have given these some other names. Okay, good. So let's write the operator here, O free particle, which is going to appear in the path integral formulation, is Im by h bar del t squared of delta t minus t prime. Since you have actually done QFT1, you probably also realize that this is the analog of the field operator, like the Klein-Gordon operator in field theory. Okay, del t squared minus gradient squared is called the Klein-Gordon operator box. This is just the quantum mechanics version of that. And you know that the Klein-Gordon Lagrangian can be written as phi box phi. That you know, I suppose. You have del mu phi, but by a partial integration, it is same as phi box phi. So that's all we are saying. We are saying that whatever is between two phi's is the operator O. Nothing more than that. Okay, good. And now we are set up with, we still haven't said anything about eta. It's this d eta, it's a measure. We still don't really know what the measure is, but whatever it is, we want to integrate it over a Gaussian. And so we can be quite brave and say that this thing should be det to the minus half of O t prime upon 2 pi by the rules of Gaussian integration. Okay. Now so therefore the quantity we are trying to calculate, one part of it is this, and it's also going to be equal to product over lambda n upon 2 pi to the minus half, where O of t prime on its eigenfunctions, which I called psi n, I think. Yeah, psi n of t prime integral dt prime. This should be lambda n of psi n of t. This is nothing but an eigenvalue equation for a differential operator like O. You see that it's exactly set up like ordinary matrix equations. The only difficulty is that instead of nice indices like I and j and a sum, and this being a matrix which multiplies that, everything's continuous. Apart from the continuous nature, everything is straightforward. Okay. In fact, if we were still in that situation with our discrete time steps, then this would be all discrete and it would be much easier to do. We would have only finite number of times. So O would be Oij, where I and j label the time steps. But we made that continuous, so we are working purposefully with a differential operator. And this is the eigenvalue equation. One second. And if I can solve that equation to find its eigenvalues, then I can take the product of all of them and get the determinant. Because it's infinite dimensional, I anticipate it will have infinitely many eigenfunctions and eigenvalues. Yes.
No, I had that question only because we have now transferred the problem of an infinite product on the eigenvalues.
Yes, absolutely, and it is still a problem. We haven't got rid of it, but we've got somewhere, we have some expression. You see, I hope you can see how this is going. We're simply trying to get it into a form where we can understand what we should do next. So we are taking baby steps. Can we understand this factor? Yes, we can map it to this statement or this statement. Is there something in mathematics we can learn about determinants of differential operators or about the eigenvalues of operators, these kind of operators? It turns out there is. So there's a lot of stuff we can use. But now let's get back to this. We never calculated this and we should. So how do we calculate S classical? Well, for that we simply have to write the path. I keep looking at my notes because I'm scared of writing something wrong. The path, classical path, is simple. For a free particle, it has really no choice but to go in a straight line. And since it starts at xi and ends at xf, it's in time t, this is its classical solution. So at t equals 0, it's at xi. At t equals capital T, the minus xi cancels this xi and we get this, and capital T cancels that and we get xf. So it's from xi to xf and it's linear in time, which is what you would expect. No surprises here. And it's a very easy exercise to plug this into the action. Now you have to take x dot, square it, multiply by half m and integrate from 0 to capital T. And the answer you get is that S x classical is equal to e to the I m over 2h bar t xf minus xi squared for this path. Where have we seen this factor before?
So that should be e to the ISH.
It should be e to the I. Thank you. Exactly. So, one factor of our answer is this, and it's one factor of the correct answer. So, one more confirmation that the e to the is was the good part of the problem. Okay? The other factor of our answer, therefore, has a job to reproduce this part of the answer, and we'll continue this next time since we are out of time. But I'm not going to rush, so we'll go through this slowly till we reach the end. Though probably for convenience, the notes which I upload today probably will have the end of the derivation. So if you want to know what is the solution to the murder mystery, you can read the notes, or you can wait till tomorrow afternoon. And we'll see how well this agrees with, or how well we can evaluate this. Any questions?
Sir,
Yeah.
the calculating propagator that we divided the time interval
Yes.
to infinite parts. Why we are getting infinity? Is dividing into infinite parts is wrong, or what is going on?
Yeah.
Like,
Yeah.
is time
I-
can't be?
No, it's not wrong. It's that, I'm not really an expert, but if I can make my unexpert comment, when we learn how to integrate a function, then also we do the same thing. We divide it into discrete parts. We make a sum over the value of the function over discrete parts. The function times the measure. This is the measure, that is the function. And then we make those parts smaller and smaller, and we find that the sum becomes an integral. So somebody thereby invented a concept called integral, which is a well-defined rigorous limit of that sum. Now we need to do something similar for a path integral, and that mental step somehow is more challenging. So it's really a problem, I think, of formulating it in a mathematically rigorous way. And the thing is, if physicists could have taken the view that, well, we'll wait for mathematicians to solve this, and then when they finish, we'll come back and use it. But people are never like that. So people are impatient to do things, and the impatience leads to one result which is really striking, that part of the answer you can just get as e to the is. So you can say that, look, this was always the propagator of a free particle, but nobody realized before Feynman, maybe, that this is e to the is classical for that particle. It was an obvious realization, but only after doing all this, it became obvious. So something is fitting very well. Something else, which it doesn't look too bad, right? I mean, it's not such a complicated factor. So we have to see how well we can get it from here. It will turn out that actually can't get it directly from this, which is a reflection of the same problem. But let's leave that story for tomorrow.